Hi, that's the second example for synchronous motor. Okay, let's go ahead and read the problem here. You got a 440 volt three-phase Y connected. Any value given in three-phase machine, it means line to line always. So since we are using the equivalent phase circuit, you always convert line to line into phase by dividing to square root of 3 because you're using Y connected. So go ahead and let's just find VA. It will be equal to 440 voltage divided by square root of 3, which will be equal to 254. And the angle always, we choose it 0 as a reference here. And let's continue. The synchronous reactance of 12 ohm per phase and the armature winding resistance is negligible. So what does it mean? It means that we have only reactance, and we just add the value, which is equal to 12 ohm and per phase. Well, and the motor runs at a speed of 188.5 radian per second. So that will be the speed. We'll say if this is a shaft and you have a speed, usually, or not usually, always, it will be the synchronous speed, omega s, which is equal to 188.5, and of course it's radian per second. What else given here? It consumes 9 kilowatt. It means the stator taking 9 kilowatt. And the excitation voltage is 560 volt. That's also line to line. So to find EF, you got to take this magnitude of the voltage, 560, and divided by 3. Very important. Don't forget to do that. That will be equal to 323.3 voltage, and that's the magnitude. And always EF has a magnitude and angle. All right, what's the angle? Do you remember? The angle of the excitation voltage, always it's delta, but we don't have delta yet. So you have 323.3 voltage and the angle delta. So that's, the information. We just put it in the equivalent circuit, which is really good. And what else? Now, let's see, determine the power angle. What power angle is the same, delta, right? So we need to find the power angle delta. Well, how can you do that? All right. You remember that you can get it if you have a current. You can use the relationship of the power volts, but you don't have any information about the current. But remember that you have the power angle relationship, which is the power developed. And power developed is equal to what? If you remember the first example we solved, it's equal the input from the stator, here the armature, and you subtract the copper loss in the stator. But copper loss, it's neglected here. You can't, because RA is equal 0, so you don't have. So in this case, BD is equal the same thing as the input power. And the PD, or power developed, is equal 3, the magnitude of the armature voltage per phase, EF per phase, divided by synchronous reactance sine delta. This equation will help you to find the angle delta, because everything is given, the magnitude of the voltage and the excitation. So PD, it's 3-phase, 9 kilowatts, so you can say that's 9,000 watts is equal to 3 times VA, it's equal to 254, only take the magnitude, times EF 323.3 divided by XS is equal 12 ohm, and sine delta is the unknown. So when you do that, you will find delta, you make arc sine, and then you will find is equal 26 degree. But if you leave it like that, that will be wrong. Why? Because it's synchronous motor, and always the torque angle should be negative. So don't forget the negative sign to put it there. So we did the first part. We found that's delta. Yeah, that's, we call it power angle or torque angle. All right, or the angle of the excitation voltage. It has 3 names. So we did the first part, the power angle. We now want to find the armature current. Now it's easy. Why? Because you can use the equivalent circuit, and now EF, you know its magnitude and its angle. So now it's easy, piece of cake. We look at this one. What's the equation that you're going to use? Well, we know that the current IA will be equal, the voltage here, the armature voltage is bigger than the excitation, so say VA minus EF divided by JXS. All right, we'll just do that. So let's say IA is equal VA, and VA is equal to 254, and the angle 0 minus EF. We just got EF here, that's we have here 323.3, and we got its angle delta. Don't forget it's negative 6, and we divide by the reactance, which is equal to J12. It will give you the armature current magnitude and angle that will be equal to 12.2 m, and the angle is equal to 14.48 degree. So we can say that the magnitude of the armature current is equal to 12.2 m. All right. Now we did part B. Part C, the power factor. Okay, power factor, it's the cosine the angle between the current and the voltage. VA is always an angle 0. So if you just sketch a phasor diagram, easy one, that's VT, an angle 0, and IA, it's 14.48, it's just leading, right? So that's IA, and the angle is equal to 14.48. So it's easy. You can calculate the power factor now by just finding the cosine of the angle, cosine 14.48, and you will get 0.97. If you write power factor like that, it's not complete. You got just write leading power factor or lagging. It's leading. As you see, the current is leading the voltage. All right, so we did this part. So we finished the power factor. Now the torque developed by a motor. The torque developed means TD, and you know any torque is equal power by the speed, and always the speed in the synchronous motor omega s. And so if you want to find the torque developed, so you have to use the power developed, and we have the power developed. It's 9 kilowatt. You told me again, it's no 9 kilowatt is the input to the armature. Okay, we know that PD is equal to input. Let me just remind you, PD is equal to 3 VAIA cosine phi minus the losses in the armature, but RA is neglected, so PD is the same as the input 9 kilowatt. That's why I'm going to use it. So you have 9,000, and we'll divide it by omega s, and omega s was given in the problem, 188.5. 188.5, and you get the torque, which is equal to 47.75 Newton meter. And that's it for this example. I hope it was helpful.